Ever get the feeling that the more we learn about the universe, the less we actually understand?
Yeah, I know that feeling. It could be like, the deeper you go, the more you realize how much more there is to know.
Exactly. And today, we're diving into a concept that perfectly embodies that feeling: field redefinitions. So imagine this. You're trying to describe the laws of physics, the fundamental fabric of reality, but you're free to swap out the variables, almost like you're choosing a new language to describe the universe.
It's a really powerful idea, this idea that you can kind of rearrange the mathematical furniture, so to speak. But, and this is a big but, it comes with a catch. Because these redefinitions, as we call them, they can simplify things, make the math more elegant. But, they also have this potential to completely upend our understanding if we're not careful.
And that's what I find so fascinating about the research we're looking at today. It's really trying to establish some ground rules, for this high-stakes game of cosmic rebranding. And it does it in a way that tries to build a bridge between that familiar world of classical physics, stuff we maybe learned in high school, and the mind-bending realm of quantum mechanics.
Yeah, and what I like about this paper is that it doesn't shy away from the complexities,
Yeah.
but it manages to present them in a way that illuminates the core concepts without, requiring you to have a PhD in theoretical physics.
Which is good news for me. But okay, before we get too far down the rabbit hole, let's start with the basics. When we say field redefinitions, what are we actually talking about?
So at its core, it's all about transforming the mathematical language we use in physics. Think of it like this. You have an equation, right? And you strategically rename and rescale the variables in that equation. It's like you're finding a new, potentially more elegant way to express the same underlying physics.
So, kind of like choosing a more efficient coding language. The program still does the same thing, but the code itself is cleaner, more compact.
Exactly. And just like in coding, the real art is in making sure that this refactoring, this rearranging, doesn't introduce any bugs or unintended consequences. Because, and this is the tricky part, if we're not incredibly meticulous, we risk actually altering the very physics we're trying to describe.
Okay, so it sounds like we're walking the tightrope here. The potential payoff, the simplification, it could be huge, but the risk of messing things up, that's equally significant. So the question then becomes, why bother? Why even go through all this trouble of redefining things if it's so potentially risky?
That's where things get really interesting. You see, sometimes this process of renaming, it can unlock some incredible insights. You can take calculations that were incredibly complex, incredibly difficult, and make them significantly easier. And that can lead to breakthroughs that, wouldn't have been possible otherwise.
So it's not just about aesthetics, about making the equations look prettier. It's about giving physicists new tools to tackle really challenging problems.
Exactly. And one of the areas where this is absolutely crucial is in the development of what we call effective theories.
Yeah.
These are kind of like simplified models, right? They're designed to capture the essential physics of a complex system without getting bogged down in every minute detail.
So it's kind of like instead of using a massive unwieldy map to navigate, you create a more streamlined version that just highlights the key landmarks, makes navigation a little more manageable.
A perfect analogy.
Oh,
But, and this is important, you can imagine that the process of creating these simplified maps, these effective theories, it requires incredible precision. And that's actually where the research we're talking about today comes in. They've introduced this concept they call a classical version of the LAZ theorem. It's kind of like a safeguard, right? A safeguard for physicists who are venturing into this world of field redefinitions.
okay, so this theorem, it acts as a guide to make sure our redefined theories are still grounded in physical reality.
It's more than just a guide, it's like a beacon, right? The LSZ theorem, it comes from quantum field theory, and it basically highlights specific quantities that have to stay the same, they have to remain unchanged, even after a field redefinition. These invariants, as we call them, they become our fixed points. They ensure that we don't lose sight of the fundamental physics amidst all these mathematical transformations.
It's like having a compass that always points north, no matter how many times we redraw the map. It's reassuring to know that there are at least some fixed points in the universe.
And what's really exciting is that this research, it takes this powerful concept, this LSE theorem, and it translates it from the abstract world of quantum physics into the more familiar realm of classical physics.
So they're making this tool accessible to a wider range of physicists.
Exactly. They're democratizing the math in a way.
I like it. Okay, I have to say, I'm starting to see the appeal of this whole field redefinition thing, but I'm also really curious about the specifics. How does this actually play out in practice?
Well, to illustrate this, The authors of the paper, they use a classic physics problem as their kind of testing ground. And that problem is the anharmonic oscillator.
Oh boy, oscillators. I remember those from Physics 101, vaguely. Hopefully this won't require me to dust off my old textbook.
No, no, don't worry. The beauty of this example is that you don't need to be a math whiz to grasp the underlying principles. Think of it like, imagine a simple spring system, right? But, just slightly more complex.
Okay, so they're basically taking this spring system and renaming the variables to see if they can find a more elegant way to describe how it behaves.
Exactly. And what they managed to demonstrate is actually quite remarkable because by applying a very carefully chosen field redefinition, they simplify the equations that describe this anharmonic oscillator. But even more importantly, they show that even though the mathematical description has changed, the fundamental physics, how that oscillator actually behaves in the real world, that stays perfectly consistent.
That's really interesting. So they're essentially proving that you can change the language of physics without changing the music itself.
Precisely. And that's where this concept of normalization comes in. It ensures that our dictionary, so to speak, is both consistent and accurate.
So normalization is kind of like the quality control in all of this, making sure that when we switch from one set of variables to another, we're not accidentally changing the meaning of the words themselves.
Exactly. And this seemingly technical detail, this normalization, it highlights the incredible power and the potential pitfalls of field redefinitions. When done correctly, they can be an incredibly valuable tool. But if we're not careful, well, let's just say things can get a little strange.
Okay, now you've got me curious. What happens when we're not careful? When these field redefinitions go off the rails? Tell me more.
Imagine you're, I don't know, trekking through some dense jungle, right? And you stumble across a map, but instead of being a clear, one-to-one guide to the terrain, it's all distorted. Like paths loop back on themselves, landmarks seem to shift positions.
Okay, yeah, that sounds more like a recipe for disaster than a helpful tool.
Exactly. And that's the thing with the field redefinitions. If they're not done carefully, if that mapping between the old and new variables isn't precise, we end up with these nonsensical solutions, things that just don't make sense physically.
So instead of this clear picture of the universe, we're left looking at some funhouse mirror version. Distorted, unreliable.
Precisely. And the consequences can be pretty wild. You could have a theory that predicts particles just popping out of nowhere, or even, and this is where it gets really weird, black holes just vanishing.
Black holes disappear. Okay, now we're talking. This isn't just about, theoretical elegance anymore. We're talking about misunderstanding the universe at a fundamental level.
Exactly. And the paper actually uses a specific example to illustrate this, something called a soliton.
Soliton, that one's new to me. What is that?
So picture a wave, right?
Mhm.
Like a ripple on a pond. But this wave, it's special. It holds its shape, travels long distances without just fading away.
So not like the ripples in my coffee cup, then. Those disappear pretty quickly.
Right, right. Solitons, they're robust, they top up in all sorts of systems, and they have very specific properties.
Okay, I'm with you. But what's the connection to these field redefinitions?
Well, what the authors show is that if you're not careful, your redefinition can make these solitons, well, either appear out of thin air in your model, or just as strangely, vanish without a trace.
Hold on, you mean just by changing how we write the equations, a soliton could just disappear from existence, or even be invented when it wasn't really there?
In the context of our model, yeah.
Yeah.
Which is why this LSZ theorem and the classical version they've come up with, it's so important. It's like it tells us what has to stay put, what can't be messed with, even as we play around with the variables.
It's like having those guidelines, that stop us from accidentally drawing the map upside down.
Exactly. And this goes way beyond just avoiding math errors. It has these huge implications for how we see classical physics and quantum physics as being connected.
Okay, I was wondering when we'd circle back to the quantum realm, that's where things always get really interesting or, maybe just confusing depending on the day. So how does this research bridge that gap between the classical and the quantum?
Well, for a long time, we've treated them almost as separate worlds, right? With different rules.
Yeah.
But what this research hints at is that there's a deeper connection. The fact that this idea of field redefinitions, these invariants, that it works in both worlds, that suggests there might be a more fundamental level of description, where those two seemingly separate areas of physics, they actually come together.
So it's not just about finding a new language for physics, it's about finding the Rosetta Stone, something that can unlock these deeper truths of the universe.
Precisely. And even more profound, I think, is the question it raises about the nature of reality itself. If we have all this freedom to redefine these fundamental fields, does that mean there's no single correct picture of the universe?
Oh, okay. We went from black holes to the very fabric of reality pretty quickly there.
It's a big question, one that's kept physicists and philosophers, for that matter, busy for a very long time. But what's exciting is that this research, it gives us new tools to think about that question.
It seems like every answer just leads to more questions, doesn't it? So, where do we go from here? What are the big takeaways, the things to remember from this deep dive into field redefinitions?
I have to admit, thinking about all this, it really makes you wonder, if we can redefine something as fundamental as the fields that basically make up reality, I mean, does that imply there's no one right picture of the universe? It's a question that could keep us going for hours, honestly. Blurs the lines between what's physics and what's, like, philosophy.
Yeah.
But I think from a purely scientific point of view, it's not so much about reality being, like, subjective or whatever. It's more about recognizing that our models, they're just that, models.
So, more like we're looking at the universe through a specific lens, and we can adjust that lens, tweak it, without actually changing what's really out there.
Exactly. It's like, how do I put it? Imagine trying to describe a really, really breathtaking landscape. You could write a poem about it, right? Paint a picture, maybe even compose some music. Each one of those would be different, capture different aspects. But the landscape itself, that's not changing. And field redefinitions are kind of like choosing which language we're going to use to talk about the universe. Maybe one language is better suited for certain things than others.
Okay, that makes sense. Different ways to tell the same story, and they can all be valid. But then that brings up another question. Is there something deeper? Some ultimate truth where these fields, they are fixed, and we're just figuring out different ways to, I don't know, map them out with our math?
See, now that is the question, right?
Yeah.
The one that's kept physicists up at night probably since, well, forever. And I can't say this research gives a definitive answer, but it gives us a clue, that's for sure. Because here's the thing, even with all this freedom to redefine, there are still those quantities, those invariants, that have to stay the same. And that suggests that there is some underlying structure to it all, something fundamental that doesn't change, even if our descriptions do.
So no matter how many times we redraw the map, there are still certain landmarks that have to stay put.
Exactly. And that's what gets me excited about this kind of work. It's not just about, making the equations look nicer, though that's always a plus. It's about trying to understand the very essence of reality, pushing the limits of what we know, questioning the very tools we use to make sense of it all.
It's both exciting and a little daunting, to be honest, to realize how much is still out there. But hey, as we've seen, sometimes even the questions themselves can lead to amazing discoveries.
Absolutely. Sometimes you got to embrace what you don't know. That's where the really interesting stuff is hiding.
Couldn't agree more. And on that note, we'll leave you, dear listener, with one final thought. If even the language of physics, the very way we describe the universe, if that can be redefined, what does that tell us about the limits of our knowledge, about the nature of discovery itself? Until next time, keep asking questions and keep exploring the universe.